Hi everyone, this is Professor H. Rahman from Department of Agricultural and Food Engineering, IIT Kharagpur. I welcome you all to this traction engineering course. Today is lecture 6. I'll try to cover the mechanics of wheel and its tractive performance. So as you know, the concepts what I am going to cover is towed wheel, self-propelled wheel, driving wheel, then mechanics of traction. As you know, mechanics of traction is nothing but interaction between soil and the traction devices and the transfer of forces between vehicle and supporting surface. So based on that, we divided the wheels into 4 types: driving wheel, towed wheel, braked wheel, self-propelled wheel. And this figure we have already discussed in lecture 1 and 2. Now I'll try to give you in details how the forces are acting. So when a vehicle is moving, it is applying load to the wheel at the axle, and at the same time the soil will try to apply reaction force to the wheel at the interface. Interface means the soil wheel interface. So load from the vehicle will act on the axle, load from the reaction from the soil will be acting at the soil wheel interface. Now when you consider a towed wheel, the simplest thing is there is no torque. Torque is equal to 0 and it is unpowered. Since torque is not there, so it is unpowered. So no axial torque. So there will be soil reaction. Weight will be coming on the wheel. Weight is denoted as W. So W is acting, then corresponding to W there will be soil reaction at the at the interface. So resultant of the soil reactions at the interface is denoted as Rn. So the Rn will have 2 components. One is the horizontal component, the other one is the vertical component, which I have shown in this figure. Rnh is the horizontal component and Rnv is the vertical component. And R is acting at a distance so that the vehicle is in equilibrium. The tire is in equilibrium, and since no external moment is acting and neglecting the friction, what you can do is, if you solve this, then W will be equal to your vertical force Rnv, and the force which is required to tow the wheel forward, that is denoted as Tf. So Tf will be equal to Rnh. So towing force is nothing but the summation of horizontal forces acting opposite to the direction of motion, and weight is summation of the vertical forces. The magnitude is same, but the reactions are they are in the opposite direction. That means Rnv is opposite to W and Rnh opposite to Tf. Now if you take moment, if the point at which the soil reaction is acting is at a distance E, so then if I take moment, sum of the moments will be equal to 0. So W into E will be equal to Rnh into R. So E will be equal to Rnh by W into R. So this Rnh by W, which is denoted here as towing force by W. So this is nothing but ratio of towing force to weight coming on the wheel. Now the moment we apply little torque, so there will be shearing force acting on the interface. In this condition, there is no shearing force. In a towed wheel, there is no shearing force, but in a powered wheel or a self-propelled wheel, there will be torque acting. Now if you look at this figure, you can see there is a torque acting, weight acting on the wheel, and because of the torque there will be shearing action, so a tangential force will be developed at the interface, and the resultant of the tangential force is denoted as RT. So at the interface there will be two kinds of forces acting, one is RT, the other one is RN. RN is the soil reaction, which is radial soil reaction. Now if I resolve these forces, which I have done it in the right corner, so Rn will have a horizontal component Rnh, and it will have a vertical component Rnv. Similarly, the tangential force which is developed because of the shearing action of the wheel with the soil, so it will have two components which I have denoted as Rth, the other one is Rtv. So if you look at the forces which I have drawn here, then there you can see Rth and Rnh, they are opposite to each other. Okay, so now W is acting vertically downward. Now if you resolve these forces, what you can get is Rth will be equal to Rnh. Rth will be equal to Rnh, and W will be equal to Rtv plus Rnv. So this Rth, the thrust which is developed, that will be sufficient to overcome the rolling resistance. It will not develop any pull. And this condition we have taken as zero condition, which we have already defined, zero slip. Zero slip refers to the condition at which the thrust is developed because of the application of torque, and the thrust which is developed, that will be equal to just overcoming the rolling resistance. That means the wheel will start moving, just starts moving. Now we will move to the powered wheel. Or the driving wheel. Here two things we will be seeing. One, there will be torque which is denoted as T, and there will be a pull applied, P. So torque is indicated here, torque, and there is a pull here. Now because of the torque, there will be again shearing forces acting at the interface, and the resultant of that shearing force is RT, and the soil reaction Rn, coming from the wheel to the ground, and W is acting downward. Now resultant of RT and Rn is indicated as F. So now if I resolve this soil reaction Rn into two components, one is your Rnh, this is the horizontal component, and the other one is the vertical component Rnv. Similarly, for the tangential force which is acting because of the shearing action RT can be resolved into two components. One is the vertical component RTV, the other one is the horizontal component RTH. Similar to the self-propelled wheel, you can see RTH and RNH, they are opposite to each other. Okay. And in addition to that, if you look, P is also acting in the same direction as that of RNH. So resultant of RT and Rn, which I have indicated as F, and where the Rn will act, because there is no, here the torque is acting. So if you consider that, then to balance this torque, the Rn should act at a point so that if I extend this line, that will give you that it is not passing through the center. In case of a towed wheel, since torque was 0, it was passing through center of the wheel, but in case of a driving wheel, since torque is acting, you have to oppose that torque. So torque will be equal to Rn into this distance, center distance, the line of action with the center. So suppose that is denoted as L. So Rn should act at a certain point so that moment R will try to balance this torque. Now, resultant of Rn and Rt we have denoted as F. So F is again resolved into two components. One is your vertical component W, the other one is the horizontal component pool. So now if you look at this diagram, then simply you can write as P plus RNH will be equal to equal to RTH and RTV plus RNV will be equal to W. That means this is the weight and this is the pull, this is the rolling resistance and this is the thrust. So P plus pull plus rolling resistance RR will be equal to thrust. If I divide W on both the sides, weight of the wheel, then it becomes P by W, RR by W and thrust by W. This P by W is nothing but coefficient of traction COT, RR by W coefficient of rolling resistance and thrust by W is the coefficient of gross traction. So COT plus CRR will be equal to CGT. This is what we have discussed before and now I have proved this through the application of forces. Now let us see what are the different performance parameters now, how it is varying with sleep. As we discussed that performance parameters are your coefficient of traction, coefficient of gross traction, coefficient of tractive efficiency, then power delivery efficiency. These are the performance parameters. So now we'll see how the coefficient of rolling resistance is varying with wheel slip. The left corner figure, if you look at, this has been plotted, the CRR has been plotted for wheel slip for different soils, starting from concrete surface is the hardest surface, then dry loam, then clay loam or the marshland, then the mud. These are the four soil conditions which is indirectly representing the strength of soil. Concrete means very hard and mud is the softest soil. So how it is varying with these soil conditions I have indicated here. So in case of a concrete soil, you can see with increase in wheel slip, the coefficient of rolling resistance is almost constant. It is not varying. In case of a dry loam, it is not exactly constant, but it is varying very slightly. And clay loam also. But in case of mud or slime, you can see coefficient of rolling resistance is increasing with increase in slip. That means in a soft soil, there will be sinkage of wheel, there will be accumulation of wheel in the front. So because of that, we require more power to overcome those obstructions. That's why the rolling resistance increases, hence coefficient of rolling resistance increases. So what we conclude from here is coefficient of rolling resistance is a function of slip, is a function of soil condition. Now, if you look at the coefficient of traction COT, which is nothing but the ratio of pull is to weight and how it is varying with wheel slip, this has been plotted for 4 different soil conditions, just like coefficient of rolling resistance. In case of a concrete, in case of dry loam, in case of loamy sand, we have added one more. Then we have clay loam, then we have mud. So again, we are getting maximum COT in case of a concrete surface. And in case of mud, you are getting the minimum COT. So what happens? Why you are getting more COT in case of concrete? Because rolling resistance is less. So rolling resistance less means the thrust which is developed, thrust minus rolling resistance will give you pull. So rolling resistance is less, so pull is more. Even if the thrust is same, pull is more in case of a concrete surface. Whereas in case of mod, because of the higher rolling resistance, so thrust minus rolling resistance will reduce the pull, hence COT is reduced. This is one thing. So what we conclude from this figure is COT is also, like CRR, is dependent on factors like soil conditions, factors like wheel slip. Initially, when we increase wheel slip for all the soil conditions, we can see the rate of rise was very fast. Then after some slip, it starts almost remaining constant. But that rate of rise was very high in case of a dry soil, like concrete surface. Now, tractive efficiency. Tractive efficiency is defined as the drawbar power to axle power. So, I have given the expression for that, P by W by Q by RW, which is nothing but thrust by W into 1 minus S. That means tractive efficiency is the ratio of two powers. One is the drawbar power, the other one is the axle power. That ratio, and it also depends on the slip. Now, if you look at the plot, initially you can see it starts at a very faster rate up to this point, say, and then afterwards, initially it rises very faster rate, then after that its rise is reduced, reaches to a peak, then it goes down. So what happens? Initially, why it rises sharply? Because there is a distortion in the tire tread. Afterwards, when you further increase the slip, there will be sliding of the treads. So tractive efficiency or the output power is reduced. If you further increase the slip, the entire wheel is going to slide. Thereby, there will be lesser interaction between soil and wheel, and the power which is developed is reduced. So that's why tractive efficiency reaches to a peak at a very lower value of slip, maybe around 10%. Now, tractive efficiency can be defined by two parameters. One is, I can write then tractive efficiency is P by thrust, and then 1 minus S I can write as BA by VT. So this P by T is called the pull ratio, and BA by VT is called the velocity ratio. Velocity ratio is nothing but the travel reduction or the slip. 1 minus BA by VT is slip. So that means theoretical velocity, how much it is converted to actual velocity, and thrust, how much is converted to pull. So this is the product of these two. But if you look at this, then the losses of power is a function of, losses of power means output power, is a function of pull ratio, it is a function of velocity ratio. Now, velocity ratio, the inability of theoretical velocity to be converted to actual velocity. So as a result, what will happen? There will be slippage. There will be movement between the soil, movement between soil and wheel, movement between wheel inside the wheel. So because of that, there will be losses. Okay. Now, if I try to plot this in a different way, because this effect of pull ratio and velocity ratio, which makes this tractive inefficiency, and indirectly can say which makes this tractive inefficiency is not reflected in this figure. So that's why we will try to put it in a different way so that these losses can be reflected. Now I have plotted traction performance ratio, that means NTR versus GTR, VA versus BA by VT ratio. These are plotted against net traction ratio. So this curve, if you look at, velocity ratio is this curve, it's going down, then pool ratio, this one, so let us first and the tractive efficiency is this curve. So the tractive efficiency curve is always below these two ratio curves. And when you look at the velocity ratio, it starts nearly equal to 1 in a self-propelled condition. It is that condition we have taken as 0. So velocity ratio is nearly 1. Then when we increase the net traction ratio, what happens? The velocity ratio will go down. That means it will decrease. When you increase pull, obviously there will be more slip, hence VA by VT will reduce. Now, if you look at the pull to thrust ratio or the NTR to GTR ratio, it is nearly 0. NTR never reaches to close to GTR. So there is a difference. Why there is a difference? Because the difference will give you the rolling resistance. So that's why NTR never reaches GTR and the ratio cannot be equal to 1. The difference is roughly around on a concrete surface, it is roughly around 0.1, 0.15 like that. So as you increase the net traction ratio, the pull ratio increases and it never reaches to 1, as I said, because of the rolling resistance. So that means both the values, both the ratios are lesser than 1. So when you multiply this, then it is further reduced. That is the reason why tractive efficiency is always lesser than the ratio of NTR by GTR value or the ratio of VA by VT value. Usually this kind of plot is plotted in the right side figure which I have indicated traction performance ratio versus slip, but I have plotted in a different way so that you can verify or you can see the effect of VA by VT and NTR by GTR ratio effect on different performance of the wheel. Now this is the conventional way. The right side figure is the conventional way by which the performance parameters are usually plotted. Now what is the difference? If you look at difference, there is no difference in fact. Only the x-axis we are taking slip. In the previous figure we are taking net traction ratio. Now nature of the curve you can see it is same. Tractive efficiency is increasing, reaching to a peak at a slip value of around 10%. Then it remains almost constant. Sorry, it goes down. This one. Now, when I plot pull versus the coefficient of traction, you can see initially it rises, then reaches to a peak. So the slip at which we are getting maximum pull and the slip at which we are getting maximum tractive efficiency, they are not same. If I draw a vertical line here, then if I draw a vertical line here corresponding to maximum tractive efficiency, this is the corresponding slip. Now if I draw a vertical line here, this is the maximum pull. Now the slip at which you are getting maximum tractive efficiency, the slip at which you are getting maximum pull, they are different. So now choice is ours, whether you want more tractive efficiency or you want more pull. If you want to make a compromise between these two so that neither pull is lost much nor tractive efficiency is lost much, then you have to find out a design value. Design value somewhere here, so that not much of pull is lost or not much of tractive efficiency is lost. So you have to make a compromise. And this design value again depends on different soil conditions. What I have plotted here is only for one soil condition, that is on a hard surface. So depending on the soil condition, you have to decide whether the sleep is to be maintained at 10%, 20% or 30%. But usually we never recommend for 30%. We say that the sleep should be between 10 to 20% for all conditions, so that the maximum compromise is possible with tractive efficiency and coefficient of traction. So these are the two ways by which we can represent the performance parameters. So let me conclude then. We discuss related to mechanics of different types of wheels, then how these performance parameters are varying with sleep, with net traction ratio, and how to represent in a different way the tractive efficiency that we have discussed in this class. So you can refer to some of these books for further increasing your knowledge related to this mechanics. Thank you.